Hi, my name is Krishna. I'm a third year PhD student at Computational Science Research Center. Today, I'll be introducing my work titled Game-Theoretic NOMA Pricing to Improve User Experience and Provide a Profit in Future Wireless Networks. In a wireless network, there is a base station, and the resources available with the base station are divided into time and frequency domain blocks. When a user wants to get service, they join one of the resource blocks and get service. When all the resource blocks are taken, new users come and join an existing resource block, and the base station serves them in a round robin method. The problem with this architecture is that over 700 million new internet-ready devices were added to the network in the year 2020 alone. With such explosive growth, the round-robin method fails due to excessive wait times. NOMA has potential to decrease latency and improve spectral efficiency in future wireless networks. Under NOMA, the base station uses superposition coding, where the base station puts the signal of one user on top of the other and transmit it in the network simultaneously. The users can employ successive interference cancellation to decode their data. In order for the signal to be successfully decoded, the power has to be allocated unequally such that as the user's distance increase, the user would need more power to decode. So we need an optimal power allocation strategy. Also, under NOMA, since multiple users can be catered at the same time, there needs to be an approach to assign the users among the available resource blocks so that there's no cluttering in one resource block. And due to the unequal power allocation, the traditional pricing methods fail, and we need a novel pricing strategy. So in this work, we have come up with a new pricing strategy called NOMA pricing, which prices the QoE and not the data. For instance, consider the example of self-driving car. They require an ultra-low latency of less than 0.1 millisecond. So such an high-speed link will be priced at a higher price by the base station in comparison to a link for video surveillance or email communication, which can tolerate a delay of 1 to 2 seconds. This type of pricing is not new, and commonly we can see it in Uber ride sharing. Let's say a person has to go from home to work, they can take a Uber Express pool, which is the cheapest option, but then it's a shared ride with a walk. Or they can take a Uber Express, which is a shared drive where the user pays a little bit more to reduce the commute time. Or if the user feels fancy, they can take a Uber X, which is a standard ride where the user can keep the car for themselves and pay a lot more. So in this work, we are trying to bring such an architecture to wireless networks, and we come up with NOMA pricing framework. Under this framework, the base station can price the power unequally based on the network condition. The user can determine the amount of power to purchase based on the end application and their budget. The user also has the flexibility to choose the resource block, which gives them the best experience or economic value. In order to test the efficiency of our framework, we have simulated a NOMA architecture. In our NOMA architecture, we have one base station and 3 resource blocks with n user each. The EU or a target user can join any of the 3 resource blocks. In the first resource block, there is high interference because there are n users in front of the target user. And so the user has to purchase more power, but then the power is available at a lower cost. In the second setting, the user can purchase lesser amount of power, but then the base station increases the cost of the power. In the third setting, there is no interference at all, so the end user can end up buying very little power, but the cost of the power is higher. The objective of this research is to show that the user can join any of these resource blocks, and irrespective of the choice, both the user and the base station can achieve high utilities. So this optimization problem is solved using game theoretic methods, in particular a two-stage Stackelberg game where we formulate the base station as a leader because they know the user's buying strategy, and the user as a follower which follows the leader's decision. So here we solve the game using backward induction and concave optimization techniques. Finally, we also perform simulation using MATLAB. First, we compare the utility of the end user for both the traditional and the proposed method. In the traditional pricing methods, as the interference decreases, the utility also decreases, and the utility of the end user is not the same along the three resource blocks. Whereas in the proposed method, the utility is the same across the blocks, so the user can choose any of the resource block to achieve high utility. Similar behavior was observed for the base station as well. Here, the revenue of the base station went down as the interference increased in traditional pricing, whereas the base station can get the best profit or highest profit in all the three settings under NOMA pricing architecture. To conclude, NOMA pricing simultaneously improves the network capacity, boosts the base station revenue, and enhance the end user QoE. Thank you for listening to my talk today. If you have any questions or feedback, please reach out to me.